on this computer, and it should be recording right now. All right, so I want to review, first of all, everybody can see the PowerPoint, I hope?
Yep.
Yep, okay, so I see some head shaking. Okay, we were talking about this place in a mathematical world called Hilbert space before the break, and we said Hilbert space is this location. I'll jump to the third bullet right here. The collection of all functions of x constitutes a vector space, but it's too large. The functions that we deal with, the wave functions we deal with, the eigenstates we deal with, all those are synonyms, must be normalizable, okay? And here's what I mean by normalizable, right? What it's always meant, okay? The set of mathematical functions that have that characteristic, we say are a place called Hilbert space, okay? And it's just a restriction on all the possible functions any mathematician in the universe can think of, culled down to those which are normalizable. As we pointed out a couple times in chapters 1 and chapter 2, that means that out at infinity, the thing kind of has to blow up, or at least not blow up. It has to converge or maybe go to 0, which is the easiest way for it to be normalizable, okay? The vectors in this Hilbert space that we talked about are generally math functions like f of x or g of x, and we'll use that, okay? They're infinite dimension spaces, unlike physical space, which is x, y, z, 3 dimensions. You remember for the infinite square rule, for example, the number of states, psi1, psi2, psi3 goes up to psi infinity, okay? And they were all some constant, square root of 2 over square root of 2 over pi, if I remember right, times the sine of 1 pi x over the width of the well, sine of 2 pi x over the width of the well, all with that constant out in front. There are an infinite number of them, okay? And that's what we mean when we say these are infinite dimensions spaces. By the way, this normalizable thing, were there any exceptions we've studied so far this year to being normalizable? Anybody think of any? I'm hoping you can come up with a couple here. When was the physical wave function, the state, not normalizable? Yeah, crickets. All right, how about the free particle? Remember that was like a wave? Did it go to 0 out at infinity? It did once we turned it into a wave packet, right? Then it was kind of normalizable. So we kind of cheat a little bit. And we talk about those guys aren't exactly in Hilbert space, but they're close. And so whenever we did the scattering, there were places where it was kind of, you had like a sine or a cosine going out to infinity, after it transmitted through a barrier of some sort. That wave function wasn't normalizable. We call it quasi-normalizable. We say it's in the neighborhood of the Hilbert space, and we have some special rules that have to go on. In any event, the set of all square interval functions on a specified interval, a to b, that can be normalized are called this thing called Hilbert space, okay? And of course, the conclusion there is that wave functions live in Hilbert space. And we said this, I think, before the break, right? Couple things on notation, because most of chapter 3 is linear algebra and notation. And whenever we have these little pointy brackets, and you don't get to pick the bracket you want, you got to use the pointy ones. This guy right here, we call the thing on the left, we call that a bra, and it's got the F in it in this case. And the G thing is on the right, we call that a ket, and so it's a bracket, the closest thing we have to a humorous thing in physics, especially quantum mechanics. And you got to remember, this notation is just kind of a shorthand for this integral right here. And a couple things that you don't see, I do have my annotate pen here, you don't see a little complex conjugate symbol right here, right? No, come on, you can let me annotate. Come on back. Oh, shoot, this thing's going to be persnickety with me. Okay, you don't see a little complex conjugate symbol right there, I guess is my point. All right, can everybody still see my screen? Anybody how about Peyton's? Scream out yes for me.
I can't see the whiteboard.
You don't see the PowerPoint anymore?
No.
I see your face as well.
All right, so that means I did something. Let's share the screen again. I obviously unshared it, I guess, honest, which is not what I wanted to do. So let's reshare it. Okay.
There it is.
Yep, there it is. And now I'll blow it up again. And why is that here? Go away. Go away completely. I don't need to see you. But what I want to see is this thing. All right, there, back again.
Yep.
All right, so I guess well, maybe go all the way to there. Yeah, hopefully things will. I'll get better at this over time. Yeah, there we go. It advanced the screen on me. All right, so the notation. Don't forget that there's always a complex conjugate. It's psi star psi, right? So f of x star would be like psi star. G of x would be like psi star. I mean, g of x would just like psi, not the complex conjugate. Even though you don't write the little complex conjugate symbol by the f there, remember it's there. That's what the notation is. That's the shorthand. Okay. We talked about the Schwarz inequality the other before the break, and all we're saying is if I take an inner product and then I find its magnitude and I square it, that's less than the inner product of one of the vectors squared multiplied by the inner product of the other vector squared. Okay, and so this is written out with that notation. One of the conclusions we reached when we started to talk about this is, let's say I got GF as a bra and a ket in the shorthand notation. If I take the complex conjugate of it, it becomes FG. And so I guess I've written it the other way. FG complex conjugate, if you think about it, it just reverses which thing is complex. So in this case right here, remember F is complex, is the complex conjugate. You take the complex conjugate of the complex conjugate, it goes back to being the uncomplex conjugate thing. On the other hand, the G, which was not a complex conjugate, takes the star and it becomes the bra. It becomes a thing that is a complex conjugate. So that is one of the things about this notation. If you're doing the bra-ket notation, that means you're just doing this integral right here. We're taking the function squared and you're integrating it over some range. And remember we said this notation here, that is our orthogonality relationship. Actually, it's orthonormal relationship because this thing is equal to the Dirac delta if m and n. I don't know why there's an I there. Yeah, I had that I. It was a mistake before. It's just m and n. If they're the same, okay, that means the Dirac delta is 1. We say the thing is normalized. If m and n are not the same, we get a 0, and we say they're orthogonal because of that. And that'd be like the sine of 2x and the sine of 3x. They're orthogonal. When you do the integral, they integrate to 0, and that's one of those rules we've learned. And so you got to keep those in mind. These functions that are wave functions in the Hilbert space, we think that you can create other functions out of them, much like you can in physical space create any vector out of the 3 unit vectors, I, J, and K. We think we can create any function in Hilbert space out of this set of complete basis functions is what we've called them. All you need to know is the coefficient that you multiply them by. And that's, of course, the Fourier coefficient. And you can find it using Fourier's trick. Sorry, that kind of went by fast there, but I got to get this out of the way for the recording. Okay. And our classic example of that was the infinite square well wave functions. We said we can make any other wave function out of it. We just multiply by the Fourier coefficient. And to make it the capital psi, we throw on the time term, and then we just sum up all these terms. And we said we can find the Fourier coefficients by doing that function right there. Okay, and so we've done that a couple of times. And so this is just different notation. If you think about it, this guy right here is replaced by that notation right there, right? I'm looking for the particular Fourier coefficient. I got the function that I'm trying to create. Boom, there's the Fourier coefficient. And so, like I said, a lot of this is notation. All right, how come you're not letting me advance the screen now? There you go. We were just going nuts before, but now I can't even advance. All right, let me move this thing again. Okay, so the whole point of this, if you remember, we were calculating expectation values from literally the first week of class, and that's the little pointy bracket thing. And that's how we always calculated expectation values from the first week of class. Q here is just any operator. Let's see, which operators have we used so far? We've used position, we've used momentum, P, we've used the Hamiltonian, H. Okay, those are operators that could be here in this position Q. And if we slap them in between psi star and psi, and integrate over some range where the range is appropriate, the infinite square well, the width of the well, simple harmonic oscillator, the quantum harmonic oscillator from minus infinity to plus infinity, that gave us the expectation value. In the new notation, we'd write it like this. And I want to start drawing. Come on, let me get my annotation device. Is it over here? Yeah, there it is. So I can like start underlining things. Hopefully that'll work. Nope, not going to do it for me. Not going to do it. All right, any event, so I could just point. If I had the annotation thing working, I'd be able to actually underline stuff. All right, so any event, one of the things we believe about observables, momentum, energy, position, things that we can measure in the lab, they got to be real. They can't be complex numbers. There can be no I's involved in the expectation value. And so that must mean that the expectation value of operator Q is equal to its complex conjugate. That's how something becomes real. And so I guess what we're saying is that's how I would write the expectation value of Q. It's just that integral right there. And it must be equal to its complex conjugate in order for the expectation value to be real, right? That's why I put the little star up there. And we said that was one of the rules. If I want to rewrite this without the complex conjugate, I flop the two guys around. The thing that was a complex conjugate is no longer, and the thing that wasn't becomes, and we switch the order, okay? And so these two guys are the same. There is a name that we give to operators that have the property that psi q on psi, okay, is equal to q operating on psi times psi. We call those operators that have that property in the Hilbert space are referred to as Hermitian. And so that's a term of art, okay? And in this particular case, I've used the same function f, okay, because I was using the same psi in this example right here. More generally, I can have two different functions, f and g, if they have the property that these two things are equal. When you move the operator from the second thing that's not a complex conjugate, slap it onto the bra side, the first thing, which is a complex conjugate, if they're the same, it's referred to as a Hermitian operator. And I guess one of the questions might be, okay, is position operator, is it Hermitian? Is the momentum operator Hermitian? Is the energy operator, are they Hermitian? And the answer is, of course they are. They have to be. We believe that observables represented by, or all observables are represented by Hermitian operators. Anything we can go into the lab and measure, because it's real, must be represented by a Hermitian operator. Any questions so far? I'm just kind of yakking away here. Okay, little proof of one of them. Okay, is the momentum operator Hermitian? And so this is what we said we would do to check this out. We're going to say, okay, I got F, and then I got the momentum operator operated on some other function G. Remember what that means. That's shorthand notation for this. You can see why this notation gets adopted. This is unwieldy if you're doing it all the time, and this is your field of research. Remember, the momentum operator is minus IH bar times the derivative with respect to X. Okay, and so I've got to do that integral. Can anybody look and tell me how I did that integral right here? What method that you learned in a calculus class am I using? And I'm not moving on until somebody shouts out an answer here.
Integration by parts.
Absolutely, right? So what does integration by parts effectively do? I take this thing and I integrate it, and it becomes G. And I take the other thing, F star, and it takes the derivative. I've got the constant I've got to play with, and then I got to make sure I got this guy in the right place. Now, notice integration by parts then becomes these two guys, F and G multiplied together with the constant. We'll talk about why I slashed out that term in just a second. But then normally integration by parts is minus, but then the momentum operator has a negative I, and I'm taking the complex conjugate of it. So to keep it minus I guess I had to flip that sign over to be positive, okay? And hopefully you're able to put up with that little trickery that I did right here. Why did I slash out what's often called the boundary term, okay? F star times G. Well, because what happens, I haven't really written something that is evaluated between minus infinity and plus infinity, right? And what do we say that the functions f and g, if they're living in Hilbert space, must do? They must go to zero out at infinity. And so that's why I was just able to cross that term just completely out, okay? It is evaluated from minus infinity to plus infinity. It goes away. And so this is what I'm left with. Now, if you notice, trickery with those negative signs. I think there were three of them that made this sign be positive to keep that the momentum operator right here, okay, with the complex conjugate. I did indeed create what I wanted to create, the momentum operator operating on the function f, as opposed to the momentum operator operating on g, by using the integration by parts trick. And so I found that these two things are equal. We said if those two things are equal, the operator in question, in this case, the momentum operator, is referred to as Hermitian. So certainly it's what we expect. We're able to observe momentum in the laboratory. We're able to measure it in the laboratory. We fully expected the momentum operator then, and therefore the expectation value that we get from using the momentum operator, to be Hermitian. Okay. All right. I guess to be fair, and I got to get our pictures out of the way here for the recording. So give me a second just to put them up to the top. There we go. I can move by clicking right there. Okay. And we're really talking about complex conjugates because I'm just thinking about integrals and functions. But Hermitian conjugate is referred to as the adjunct. If you remember when we were talking about linear algebra, the adjunct is both the complex conjugate and the transpose, right? And then that was just me flicking my finger really lightly on my mouse. Then you use the dagger symbol instead of the complex conjugate symbol, because if you actually had a matrix here, as opposed to an operator that was a matrix, you would have to both take the complex conjugate and take the transpose of the thing. And then we'll come to find when we start talking about operators which are matrix-like, that a Hermitian operator is equal to its Hermitian conjugate. I guess being equal to its complex conjugate is just a special case of that. You haven't done the transpose. And everybody knows what transpose is. Remember, that's flicking something that used to be in a row and you move that into a column. So you take element 1, 2 and you put it in position 2, 1. You take element 1, 3 and you put it in position 3, 1. So you're basically flipping the non-diagonal elements of a matrix around. And so a more general definition, I guess, is that a Hermitian operator is equal to its Hermitian conjugate. Good to go? All right, moving on. All right, I guess since I'm talking about matrices a little bit, I want to think about expectation values in this notation and kind of write it out. We said that any wave function can be a Fourier transform of these basis vectors, like in the infinite square well, the sines and cosines that we talked about, with the Fourier coefficient. And the bra, the other side, the thing that I'm gonna pre-multiply by, of course, is a complex conjugate. Don't forget this psi sub n here is also complex. The notation just doesn't require you to write it. It is there, okay? And so then if I'm trying to find the expectation value of Q, I would let Q, probably should have put a caret right there, operating on the ket and pre-multiplied by the bra. Notice I use different indices just to be as general as possible for these things in the bra and the ket. Okay, I used N for the one that's in the ket and M for the one that's in the bra. It would not make sense if you were to try to write it out, okay, to have the same index there. It would just be too confusing. You could use I and J if you want. I chose to put M and N as my indices. Okay, and this time I did put the little hat on the Q operator right here, and I can always bring the constants out front, because remember, this notation is shorthand for an integral. Okay, so if I believe these are constants, Fourier coefficients are constants, I can bring them outside, and so that's what I mean by this little bracket with the Q operator, the expectation value of Q, right? Okay, and so now I got to move these guys up to the top because they're in my way, and so we've basically created right here a matrix element M and N, and so you tell me M is equal to 1, N is equal to 1, M is equal to 2, N is equal to 2, M is equal to, I think I said 1, N is equal to 3, M is equal to 1, N is equal to 4. How many I ever go? Then I go on to the next M, 2, N is equal to 1, 2, 2, 2, 3, and so forth. You could see I could create Q as an infinite dimension matrix that looks just like this. And that is how you can calculate an expectation value if the Q happens to be in matrix form. And I kind of wrote it in the order you would do it. It's not critical that you do it in the order like this, but I think it makes more sense. And why I say that, okay, now it's not going to let me advance. Because if you were multiplying a matrix times a vector, and now I really do want to be able to annotate. So I'm going to find that pen and make it work regardless. Okay, so come on over to here. Come on, pen. Why are you not letting me write? Well, you know what I'm going to do? I'm going to switch over to.
Wait, what's the pen in the lower left-hand corner?
I don't have anything in my lower left-hand corner.
Oh.
Yeah, it's interesting. Do you have something you can write with? It'd be handy to have. Yeah, the host gets a slightly different screen, which is kind of annoying me a little bit right now.
Try moving the mouse just down to that lower left corner.
Yeah, when you change your slides, there's like a pen mark right by the arrow.
Okay, now I don't even have a mouse right now, and I don't know what I did there. I completely lost my mouse. Yeah, I'm frozen here. Yeah, that's what I always worry about that. All right. This has happened to me before. Maybe I should have restarted my computer at the beginning of the day just so that things are working better. All right, I'm going to try to get out of here. That's not letting me do that. I don't have a mouse. I got something up there, though. I'm going to go to new share. All right, good. Maybe even though I don't see the mouse, I can get over to that guy. And then I can use my finger again. Come on up. There it is. I got my mouse back. That's good. All right. So,
Yeah, so you see in the lower left-hand corner?
Right there. Yeah, maybe. Okay. Let's give it a shot. Let's make this go away. Oh, well, now I can't do that. All right. We'll get out of there. Okay. But I can move it, I hope. Can I make it? Can't minimize that. Why not? Can I make it smaller? Yep, I'm making you go away. All right, so you're talking about this guy down here, right?
Yeah, we lost the whiteboard again.
Okay, can you see my PowerPoint?
No, that's what I mean.
All right. So let's boop, 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 boop. All right, so let's go to, nope, I don't want subtitles. I want to go, all right, go ahead. No, stop, Microsoft's got it, go away. And show, there we go. All right, that's good. Now let me find Zoom again. And I see Peyton right in the middle of the screen here. Yep. All right. One of the things I don't like is it's really the Mac interface. Makes me wonder if I had a PC, if I'd be happier. All right, minimize that. I need my control panel. No, not that. Where are you hiding it? Where are you hiding it? Okay, there's you. There, no, make it full screen. All right. Yeah, this is irritating. Really, oh, there it is, share screen, it's back. Yeah, so let's see, go back to the PowerPoint, share that, and bring that up. And I was on this page. All right, I see Peyton off in the corner. There's a little button. Let's see if it'll let me write.
Oh, there was the,
By the way,
yeah.
for future reference.
Yep, all right. Say that again.
For future reference, I was just notified that the keyboard shortcut for Macs to get back to screen sharing is the Control-Shift-S.
Control-Shift-S? Good to know.
Yeah.
Control-Shift-S.
Or
All right.
Command. I think that's what it's called on Mac, not.
Okay, excellent. All right, pen color. Yeah, that's good to know. We'll see if it works for me. All right, it looks like I have a pen tool. So what I want to point out about this guy right here, and the reason what we're talking about is why did I choose to take the two coefficients and separate them out on the previous slide? Okay, see, I had written the two Fourier coefficients, the complex conjugate and the non-complex conjugate, right next to each other. And then when I turn this guy right here, this integral, into this matrix QMN, I brought the n over here. I think it's more logical to write it that way, okay? Because if you were actually doing a matrix, okay, you'd have Q11, Q12, Q13, right? And Q21, Q22, Q23, dot, 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 dot. We'll just kind of do that. And then if I was multiplying it by A1, A2, A3, you'd write it over there. And then I think most people would say the answer to that is in the first row, it'd be Q11 times A1 plus Q12 times A2 plus Q13 times A3, right? That Q is getting pretty lousy, but that's what I'm talking about. That'd be the first row. The second row, of course, would be Q21 times A1 plus, and hopefully you got the point here, and then there'd be a third row, and then however many I wanted. And that's why I think it's more logical to put the A there. If you're doing the full expectation value, you would take this thing and you would pre-multiply it by B1, B2. I don't know why in the world I put the brackets like that. It was just kind of a wacky thing to do. Okay, there's your vector B right here, right? And then having already multiplied Q by A, I would have that guy sitting right here with the Q11 times A1 plus Q12 times A2 plus Q13 times A3, and the next row and the next row, which I'm too lazy to write. And so, of course, I'd multiply B1 times the first row, and then I'd add to that B2 times the second row, which I was too lazy to write, and B3 times the third row. And hopefully you can see when I'm done with this, I'm just getting a number, right? There's no longer a matrix. It's just a thing, okay? And it could be an expression, but it only has one element. So I've collapsed something that was an infinite dimension column vector times a two-dimension matrix when I did this. And then if you pre-multiply by B, okay, another vector, but this time I would make it a row vector. Once I'm done doing the math, all I should have is a single element. I shouldn't have any kind of an array of elements. And that's the picture that we're trying to describe here. And that's why it is just an expectation value, a number, just like you've been calculating all through the semester so far. Any questions on that? It was kind of rough with me getting set up here, and I apologize for my Zoom I guess it's lack of kind of experience. Yeah, go ahead, Jake.
Can you go back a slide or two real quick? Yeah, right there.
Okay. And the one mistake I think I should have an operator hat right there. It's not always necessary, but it absolutely is necessary right there. Anyway, go ahead, ask your question.
I just missed one of the variables, but I'm good now.
Okay. And by the way, all these PowerPoints are shown as PDFs in Canvas. And we're recording right now, so you can always come back and look at it later if something I said wasn't clear, or you missed it the first time, you want to hear it again. Of course, you won't make it any clearer if you didn't understand what I said the first time, but that's sort of it. All right.
I have a question really quick.
Yeah, go ahead.
So why did we adopt the notation of like the double arrows over the Q on the last slide?
Yeah, I've seen that. That's this right here is the symbol you're asking about.
Yeah.
Okay. If you do that, it's a vector, right? Just a one dimension thing, either a column or a row. And that's what I'm putting over the A and the B. If it's a two-dimensional thing, the notation that I'm used to seeing, and and I've never had linear algebra, but it's a double arrow. It's like a tensor, right? So this symbol right here over something is for a tensor, and that means something like this. And in our case, it's very often going to be just a two-dimensional thing, okay? But it could have an infinite number of rows and an infinite number of columns, but it's still only two dimensions, as opposed to like a third-rank tensor or a fourth-rank tensor that has three subscripts or four subscripts, right? Is that new? Have you never seen that? Because space-time uses that notation too very often.
Yeah, I've studied tensors, but I just didn't. I've never seen that notation.
What notation have you used for tensors? I'm kind of curious.
Oh God, it's been a while. I mean, I think for explicit tensors, that's what you'd use.
Right.
I just usually use index notation.
Yeah, sure.
Hard to specify it's a tensor.
The easier way to do it is just not do this at all, right? And M and N or I and J or something like that, right?
Mm-hmm.
That
I get why you did that, because like, tensors follow like certain rules.
Right.
So it's not just a regular matrix.
The row by column multiplication in matrices, just any old matrix, is what we're going to be following here. Okay.
Mm-hmm.
Yeah, if you want to write it out explicitly with the indices, that works too. Right. And this tells you it's a two-dimensional matrix. Put a third indice, whatever you need. You can have fourth rank tensors, but we're probably going to be restricted only to two-dimensional tensors. All right. Yeah. So one of the things we found out is we call this guy an eigenvalue equation, right? And this could be like the Hamiltonian is equal to the eigenvalue, the energy eigenvalue, times some wave function. And if you think about it, the Hamiltonian is exactly Schrodinger's wave equation, right? And then you have the energy eigenvalue E times the wave function. And so apparently here, the expectation value of this operator is this thing we're going to call Q, right? And if we're talking about the Hamiltonian, this would be the energy eigenvalue. If we're talking about momentum, I guess this would be the momentum eigenvalue, which we don't really have a symbol for, I guess. And I think one of the things we did a couple times is we found what the expectation value of the operator squared was. Okay, and so that means you're doing the operator twice on this wave function right here. And so I did it the first time, I just brought out a Q. Remember, this is an integral. This is shorthand for an integral. So I bring out a Q. And then if I do it again, it brings out a Q squared. And if psi star psi is normalizable, because these two guys are the same thing, well, that just becomes one. And what we've said is the uncertainty in whatever this this operator is just the expectation value of Q squared minus the expectation value of Q quantity squared, and you take the square root. If you don't take the square root, it's the variance. And what you can see here is for a lot of operators, we found that these two guys, when you subtract them, they're the same. You get zero for the uncertainty. And if that's true, then we say the wave function we used in the eigenvalue equation, that is a determinant state for the observable Q. And you realize you've done this math sometimes, and sometimes it doesn't turn out to be zero like it does here. But if this happens, like I've shown here, then we say that this being the uncertainty is equal to zero, then we say that function is a determinant state. That eigenstate, that eigenfunction is a determinant state for whatever the observable is, whether it's energy or momentum or position or any of the operators we're going to be using for the rest of the semester. Okay, so for any observable, there's a set of states that are determinant for that observable. And these are just the eigenstates of the Hermitian operator associated with the observable. And so we've been doing Schrodinger's time independent wave equation, which is an operator, right? It's the Hamiltonian operator. We've been getting an energy eigenvalue. And what we've always been doing is solving for what the determinant states are. We call them the eigenfunctions that are the basis for that particular potential set, okay? And so determinant states of total energy, they're called stationary. We've used that word before. doesn't necessarily work for other observables other than energy and Schrodinger's wave equation, unless those those operators are also determinant for the energy eigenvalue. And so I guess, you know, the square root of 2 over a times the sine of n pi x over the width of the well, that guy could be a determinant state for another another operator other than the energy operator, which it clearly is a determinant state for, if that other observable is also determinant for the energy eigenvalue. And often it won't be, but it could be, I suppose. And so we just leave that as a possibility. All right. So determinant states, it's what we've been solving for when we solve the problems we've been doing all along in the semester. We're just kind of giving it some new notation. Now, a couple things hopefully we've noticed about eigenvalues and eigenstates in chapters 1 and 2. Okay. We already said any given Hermitian operator has a particular set of eigenvalues and eigenstates. Great. The eigenvalues can either be discrete, continuous, or some combination. And our examples that we've done so far of discrete eigenvalues, discrete values of energy, are the infinite square well. Remember, E sub n was something like pi squared, n squared, h bar squared over 2m times a, where a was the width of the well squared, right? And so for particular values of n, you got particular energies. Harmonic oscillator was something like E was, sub n was equal to, I think, n plus 1/2 is what my memory is. And I think I got it right here. Remember what that's multiplied by? Yeah, h bar omega, right? And so the point is, I guess, there isn't a continuous set of energies. They're very discrete. They existed where n is equal to 1, where n is equal to 2, and so on. There were also eigenvalues of continuous, that were continuous. And the example that we did of that was the free particle. And sometimes after we're scattering, well, you might have a combination, because inside the delta well, for example, you had discrete energies that looked like the infinite square well, but outside it was more like a scattering problem, and the energies were continuous. Okay, and so those are the combinations, the possible things we can have: discrete energy eigenvalues, continuous, or some combination of the two. Within the discrete category, there are two types: those that are degenerate and those that are non-degenerate. A degenerate eigenvalue, you might remember from modern, is if you have an eigenstate and another eigenstate, and both of those states yield the same energy eigenvalue, okay, we refer to that case as being a degenerate eigenvalue. Okay, so a kind of a common thing is you might have a two-dimensional eigenstate, and maybe, I don't know, this is one eigenstate, and this is the other eigenstate. They're different. Okay, they're orthogonal to each other, but if they happen to have the same energy, we refer to them as being degenerate. Okay, and that's an example, and I think we saw in modern. I don't know if Campbell's folks who took modern from Campbell's talked about that, but it's out there, and we have to deal with it. Okay, these sets of eigenvalues that are discrete or continuous, we refer to as the spectrum. It's kind of related to the spectrum of light. And you remember, it's not exactly the same as the spectrum of light, but if this is energy 1, and this is energy 2, and this is energy 3, remember the spectrum of light is the transitions between these guys, right? That's how we get the different colors we see, okay? And in quantum mechanics, though, we refer to actually the energy itself as the spectrum, as opposed to the frequency of the light you get as you transition between the energies. So they're related, but obviously it's a different thing. The folks who did the spectroscopy and looked at the lines of the hydrogen lamp were thinking about this change between two energies. And when somebody who's studying quantum mechanics talks about the spectrum of eigenvalue, they're referring to actually the energies themselves. They're talking about these lines that I've drawn right here, as opposed to the transitions between the lines. We believe eigenstates form a complete basis, okay, which means, of course, that any other state can be expressed as a linear combination of those states with the appropriate Fourier coefficient. You could prove that. We're not going to for finite dimension eigenstates. It's taken as an axiom for infinite dimension ones, and that's all I'm going to say about that. I guess discrete spectra have normalizable eigenstates. We've said that the eigenstates have real eigenvalues. I guess here's the proof. If I take an operator on a wave function and I get the eigenvalue times the wave function back, that's the eigenvalue equation, then I can pre-multiply it by the state. And I guess I can take the complex conjugate, because that's the same thing as this. I just noticed reverse the order. What was here became right here, okay? And that gets me Q complex conjugate. For any Hermitian operator, we said those two guys were the same. If this guy and this guy are the same, the only way those two can be the same is if Q is real, okay? And we said these two things have to be the same if the operator is Hermitian. That was our definition. It's a little bit of a circular argument, but we are saying that the eigenvalue has to be real. And that really shouldn't surprise anybody, I don't think. They're also normalizable if they're distinct, okay? You've got a problem if you've got discrete eigenvalues and they're not, if they are degenerate, and we're going to have to talk about them. So distinct is a synonym for non-degenerate. Degenerate would be having two states having the same eigenvalue. But if they're distinct, okay, you have to have orthogonal eigenstates. And again, we're doing the same thing. We've got two different wave functions here, f and g, just different math functions. And I'm saying that I get an operator q if I operate on the f function. I get a different eigenvalue if I operate on the g function, okay? And so f operator on g, which would be, I guess, the expectation value of q, is going to be equal to q prime times this guy. And if I go the other way, I go q on to f, which is the same as this, okay? Flipping the order because of the complex conjugate, okay? Then I get the complex conjugate of q times this guy. And I guess I can flip the order again to get rid of the complex conjugate. The math here is kind of, it's just a matter of paying attention to order, really, is what makes the mathematics work. And so Q being Hermitian, this thing right here has to be equal to that thing right there. And I did the tricks that I'm allowed to do because the operator is Hermitian, and the thing that we said with linear algebra you do when you take a complex conjugate, okay? But these two guys have to be equal, as I said, so I can bring that to the other side of the equation, take the two eigenvalues, find the difference between the two, and factor out this f star times g integrated over dx. Don't forget that's what that means, right? We're saying f star of complex conjugate g times dx, right? Okay, I factor that out, and I'm saying, okay, if the eigenvalue q is real, well, that takes care of the complex conjugate. But if they're distinct, well, q is not equal to q prime. They're two different eigenvalues associated with both f and g. Something here has to be 0, and it's that guy, which means f and g must be orthogonal. Okay, and so that's the proof that if you have distinct eigenvalues, not degenerate eigenvalues, the wave functions associated with them have to be orthogonal. Okay, and that's what we're talking about. And that may not be something that if I just told you it was true, you might have believed. And I'm going to cut it off here today because I've been babbling long enough. But what are we going to do for the discrete eigenstates if we have degenerate eigenvalues? And the answer is going to be something I'll show you on Wednesday called this Graham-Schmidt procedure. And I've deferred talking about it for a while, but it is a way to take non-orthogonal wave functions that you would get from degenerate cases and turn them into an orthogonal basis, because you need an orthogonal basis in order to be able to create any other wave function that might exist in the Hilbert space. All right, that's a mouthful. A lot of it's vocabulary, a lot of it's notation. I think the next thing to do, and we'll be doing the worksheet for both today and Wednesday, but I do have more things to do, is to stop talking and stop recording and see if you have any questions. So let me jump out of here. And we'll talk about this Graham-Schmidt procedure more on Wednesday. And pause the share. Now let's just stop the share. All right, chance for any questions. All right.
Yeah, you can make a killing with putting these videos on like YouTube or something.
You know, it is going to show up on YouTube, oddly enough, but I'm going to link it to the Canvas site so that if you do want to pull this up later and see how I babbled and said the wrong things, you can do that. I do want to show you, hopefully, share this with you, and I'm hoping you can see what looks like your Canvas website. And this is you can see our class, and I've created a module called lecture videos. So once we're done here today, this is going to be populated with today's lesson and Wednesday's lesson and all that. And then if you're looking for the worksheets, okay, those are the two scattering worksheets that I guess, when did I make them due? They were due before breaks. I guess if you get them into me today, you can still turn them in. And then here's the formalism, okay, the Dirac notation tutorial and the matrices tutorial I may do tomorrow, because we want to be working this observables tutorial. I mean, anytime you've got today, and then of course Wednesday. And I think what you'll find as you work through this thing is a lot of it is just working with the notation, okay, getting yourself used to the notation. And there's some things that we talked about today. It's going to ask you to prove it again, prove that this is true, for example, and then you get the point. And you should be playing with the notation that we've introduced. This Bra and Ket notation, the Dirac notation that allows you to make fairly simple math proofs, which would have been a whole lot harder if you had written them out, okay? And in this case, you can see there's the Ket, there's the corresponding Bra, and it tells you to write out the expectation value. And some of that I did, but it's best if you go back and fill these in. All right, a lot of stuff, a lot of things to do. Any questions? All right, I suspect, because it's due today, a lot of people have questions on the on homework 6. And I know I helped some people with it over the weekend. If you do have questions, I'll be back for office hours at 2:30 this afternoon. And I'll be in, I'll send you another, I think I actually have sent you an invite for another Zoom meeting. And any questions that you have on the homework 6, which is due today, I'll be available for. Tomorrow, I'll be available for office hours for the worksheets on the matrices tutorial and the Dirac delta notation. Questions? Chance to answer things before? Yep. Is that a Peyton raising his hand?
Yeah.
Okay. Let me
It's
stop.
just kind of like a thing. I'm kind of shaky on how you just kind of said we're just gonna let Q be an infinite, like how did you arrive at the notation where Q is a tensor in the first place? Like I get like how, like why it, like not why it's a tensor, like you just kind of said like let's just make an infinite dimensional matrix.
Yeah, and that's if you need to, is I guess the answer. And in none of the problems that we've done up to this point in the course did you ever need to, right?
Mm-hmm.
But I want you to think about and why infinite, because for example, in the infinite square well, how many eigenfunction, how many energy eigenfunctions do you have? The answer is an infinite number.
Yeah.
And I guess, what if you had a particle and you needed to make it into a matrix because you had something like spin, where you had a couple different states, and each state might have an infinite number of eigenvalues depending on how you constrained that thing.
Mm-hmm.
And so all of a sudden you can see that you can develop out an operator that would have to take an infinite number of possible states, and then you can have like an upstate, a downstate. The nuclear people get nuts with this. You can have these charms and colors and all that for different states. And you might need a situation where you have to make Q more than just something simple like we've done, where Q is either an energy or a momentum or a position, right? Mm-hmm. So that's all we're trying to set up, is if you needed to do more with this because you were working a way more complex problem, the machinery is in place. And that's really all we're saying.
Okay, so basically you can just kind of create a tensor by sandwiching an operator in between bra and a ket.
Yes. And then you can get every element that could possibly exist for whatever problem you're solving by doing that mathematics for every matrix element. And since the size could be infinite, right? You can go 0 to infinity, you can have an infinite tensor because of that.
Awesome.
Yeah. And, are we ever going to do that? I don't know that I have a problem that we're going to get to this semester.
Yeah.
But it's, it's out there.
Cool. Thank you.
All right. Others? All right. Well, yep. Another question? If not, we'll call it a day. You'll see this being posted up, and I'll be available this afternoon to help you get started on the worksheet, which ultimately will be due Friday, I guess, the one for today on observables and observables as Hermitian operators. We'll work on it today and Wednesday. I'll have more to talk to because what haven't I said anything about yet? I talked a little bit about discrete eigenvalues. I haven't talked at all about the continuous eigenvalues. That's what I'll be talking about on Wednesday. And we'll also talk a little bit about what to do with that degenerate discrete eigenvalue. We'll talk about the Graham-Schmidt procedure and how that goes. It's just a mathematical thing that you do, but and it's actually the last problem on the worksheet. That's why I'm going to defer it to Wednesday. All right, pen in questions. That's it. We'll see you all on possibly this afternoon for some help with the homework or anything else. Otherwise, I'll see you Wednesday at 11:30. Talk to you then.
Yeah.
Bye-bye.